All right, back from break. We're into chapter 21. We said there's a lot of stuff in 21, so if it seems like there's a lot of stuff, don't panic, there is. And it's a lot of important stuff, so we want to be moving through this and making sure that we're clear on the important items that come up. We said that there is an electric force in nature that depends on the center-to-center distance between two objects. It depends on how much charge the two objects have. And we said that later on we're going to see that it also depends on the velocities of the two charges and their accelerations. We need to know all of that information to get the electric and magnetic forces fully calculated. We said though, but for us right now in chapter 21, we're going to ignore velocity and acceleration effects and just treat the objects as if they're just sitting there at rest. And the force then is given by k q1 q2 over r distance squared, where r is the distance, center to center, q is the electric charge of each of the two objects, and k is what we call the electric force constant. Okay, so that's the fundamental pattern, or the formula that we're going to be using to do all of our calculations. Now let me step through this. This is other stuff we've talked about. We had made it all the way to this example. So we were looking at three charged objects, also known as three charges, set up all along one line, and we had just gotten through calculating the forces between those. And we said that the idea here is to draw a couple of diagrams, really. We drew a diagram here, and I probably didn't need this one too, but once I got a little more experience. But for right now, I'm going to say object 3 is going to experience two forces, one from charge 1 and one from charge 2. And then we went through and did the calculations and ended up determining what the direction and the magnitude of the net force would be. Now, what many of you are probably thinking to yourselves is, well, wait a minute, we only solved for one of the charges. What if the question asks, what's the net force on charge 2? Well, that would be another set of calculations. We would follow the very same formulas, but let's just very quickly ask ourselves, what are the forces acting on charge 2? And charge 2 is experiencing a force due to the presence of charge 3, and it's attractive because they're opposite signs. So there's going to be a force 2-3 in this direction, and then there's going to be a force 1-3 in this direction because this central object, the positively charged object, is going to experience forces in opposite directions because it's going to be attracted to the other two. So if we wanted to go back and ask what's the net force on charge 1, what's the net force on charge 2, those calculations would follow the very same reasoning that we used for charge 3. Okay. All right, that's how this works. Okay, here's one more example that is, I'm going to say this one's a little challenging. We're moving into 2 dimensions. And so what we've got now is the example they've given us here, 21-3, is looking at the electric forces acting on, well, we're going to see which one it is. Anyway, we got an object 1 with charge 1 here. It's negative, so label that negative. This one at the corner, or this one at the origin, is positive, and that one's 50 microcoulombs. And then another charge here that's positive. Now, they could ask about the net force on charge 1 or charge 2 or charge 3. Which one did they ask about? And it looks like they're calculating the net electric force on charge 3 due to the presence of charge 1 and charge 2. So we draw a circle around charge 3 and ask what forces are happening. And what's happening is there's a force coming, well, as a result of the presence of charge 2, there is a force in this direction. Now, these two charges are both positive, and that's why the force is in a repulsive direction. So charge 3 is going to experience a repulsive force, a force directed away from charge 2. And so they've drawn that in. Now what also is going to happen here is that there's charge 1, which is negatively charged. And so negatively charged means that it's going to be attracting this positive charge. So there's going to be a force pulling charge 3 towards charge 1. Now for this force, it's tipped at an angle. So that's going to require us to do determine some vector components and add vector components together. This is going to require the techniques of vector addition, which we certainly did a lot of in 3A, in Physics 3A. And so this is showing up again. I guess we didn't do a lot of this later, in the later chapters, or did we? I mean, where we were doing force diagrams really goes all the way back to maybe chapters, certainly the fluids, chapter 13. Anyway, we're back to where we're going to be doing, for better or worse. If force diagrams were like, yes, this is what I really like doing, then hey, we are back doing those force diagrams. If it wasn't your favorite, here's one more chance to let force diagrams be your friends. And anyway, in any case, what's going to happen here is we are going to be putting together some force diagrams. So let's see what that looks like. Let's look at what a solution might be here. So here are the net forces. Object 3, which is located here, is getting pushed away by object 2, but it's being pulled towards object 1. And so I'm going to have a force between objects 2 and 3. And again, I could write this 2, 3, or 3, 2 because I'm letting my diagrams keep track of directions. The directions are already shown. And then force 1, 3 is going to be in that direction. And there's going to be an angle. So we have to, did they tell us what the angle is, or did we have to calculate it? They told us the angle. So that angle is 30 degrees. And so what's going to happen here is that force 2, 3 is going to be given by k, little k, the force constant, times q2 times q3, I got those multiplied together, divided by distance. And the distance here was 30 centimeters. The distance here is 60 centimeters. This is a 30-degree triangle, so the hypotenuse is twice the distance of the shorter side. Anyway, that worked out to be 325 newtons. So that's, that's a lot of force. F13, the strength or the magnitude of this force, worked out to be 410 newtons. So what I've got is I've got 325 newtons pointed in that direction, pushing on that charge, and then I got 410 newtons pulling on the charge in this direction. I have to do vector addition. So what's the total force acting in the x direction? Well, if I look at my diagram, F23 doesn't have any contribution in the x direction, but F13 does. F13 will have a cosine 30 degrees component in the x direction. So I'm going to get the x component from this, and that's going to be my net force. Now, I already solved for F13. That was kind of the preparatory work that I did over on the left side underneath that diagram. So I know what F13 is. It's the 410 newtons. So 410 times the cosine of 30 is leaving this, and now I'm actually, I gotta go back and double check numbers. Cosine of 30 is, it should be larger than this. I gotta go back and check numbers on this one. Okay, I think I'm gonna have to do that. I'm sorry about that. I'm just looking at numbers. And so I guess what I'm saying with this is be careful in your calculations. Look at the numbers that are coming out and make sure that they're making sense. So I do try to double check everything, but I think this is one that may have slipped through. So I'm going to go back and double check these numbers. For Fy, the formulas look good. For Fy, I'm going to have something that's F23 minus, now notice that force 13 is going to have a component in this direction. And that's going to be a component that's the sine of 30. So the formulas look good. But as I'm saying, I'm going to go back and double check the numbers that, that I've ended up with for this calculation. Okay, and if I do end up doing that, I'll just make the changes to the slides, and then you guys can watch for the corrected numbers. Let's look, assuming these numbers that we've ended up with. The net force then would come from taking fx squared, fy squared, combining those, taking a square root, that's going to give me a net of 288. And then the direction on this force would be taking the inverse tangent of fy over fx. Now notice this angle, of course, is different from this angle, so I've determined a new, a different symbol. I'm using phi for this angle. So what I've ended up being able to do here then is getting a net force and getting an angle, and just one more statement of, I've really got to go back and double check those numbers because they look like they're off to me. Okay, and I will do that. All right, so those were all examples. Kind of everything we did in that last section was looking at how we're going to do electric force calculations based on individual point charges. What we say is kind of a concentration of charge here and a concentration of charge here. Those are referred to as point charges. Now, if you remember, I was using this phrasing. Let me see if there's a good picture I can come back to, where I was saying things like object 1 and object 2, they both have charges, and there will be a force on object 1 due to the presence of Q2. There will be a force on Q2 due to the presence of Q1. Now, kind of thinking in those terms, what I want to do now is move on to the next topic, and the next topic is going to be introducing something we call the electric field. And what it says is this. Here is a negative point charge. We're going to start looking at some point charges. We're going to be looking at more complicated charge distributions as we go along. And so we're going to get to more, but we're going to start off just looking at individual points or little tiny kind of spherically shaped charges. Those are the easiest ones to start with, and then we'll look at some more difficult ones. So here's a positive charge, here is a negative charge. And what we're going to say is, here is a location in space. Here is a charge. Here is a location in space. If I have just one charge by itself, I don't have any forces yet. But what I can do is I can kind of anticipate what might happen. Let's say I have a charge here, and I have a point in space right here. What would happen if I put a charge at point A? Well, if I put a charge at point A, it would experience a force. What direction would that force be in? So I already have one charge located. I'm going to bring in another, let's say it's a positive charge. If I bring in a positive charge and place it at point A, that's going to experience a force due to the presence of a positive charge that's kind of already there. And as a result, there will be a repulsive force, and that charge will be pushed in that direction due to the presence of this charge. Now notice, what if I brought in a different charge? What if I brought in a negative charge? Well, if I bring a negative charge in and place it at point A, it's going to feel a force in the direction towards the positive charge. So what we do is we say, okay, let's just start with one charge and say that that one charge already has the possibility of exerting forces on other charges. We say that that's due to its electric field. So we say that a charge, just sitting there by itself, no other charges around, has an electric field. It's kind of like saying, here is planet Earth. What kind of a gravitational force will it exert on objects? And then starting out and saying, well, planet Earth just has its own gravitational field. And as objects are brought in the region of where planet Earth is located, any object in that region will experience a force because Earth has a gravitational field. So rather than use a direct force calculation, we introduce this idea of a field. It turns out it's useful because once I have a charge here, I can say it has a certain amount of electric field, and then I'm ready for whatever happens. If different charges come in, I can use that electric field to more quickly calculate what force we'll have. We'll look at some examples and see how that works. Now the way we have to, because charges can be positive or negative, we have to be a little careful about how we define the direction of the electric field. With the gravitational field, it was easy because gravity is always attractive. And so for a gravitational field surrounding a planet, we just say the gravitational field is directed towards the center of the planet. But for a positive charge, we say that the electric field at every location in space is pointing away from the charge. Now, it's not something that's leaving the charge. It's not something that's radiating away. It's an influence that it has on its environment, or it's an influence that it has on any objects that happen to come by. And so these arrows just represent the possibility of a force taking place. For the negative charges, I can define E fields the very same, using the very same picture, except we just turn the arrows around and say that the direction for an electric field surrounding a negative charge is directed towards the charge. And here, for the positive charge, it's directed away. Again, it doesn't have to do with anything arriving at or leaving the charge. It's just the direction of the force if a positive charge were to come and be placed at one of these locations. We use positive charges as kind of the default for defining all of our directions. And then we say if any negative charges are involved, then we have to flip directions based on how many of those charges are negative. So the electric field is showing the influence a charge has on any other objects that come into its environment. The electric field is a vector. You can see that it has direction to it. And it's located at every point in space. The electric field closer to a point charge will be bigger. An electric field farther away will have less of an effect. And then the direction is pointing away from the positive charges, pointing towards the negative. This last item here says that since they're vectors, you could imagine dividing this up into components EX, EY, and EZ, which we will not do. So we're not going to be looking at three-dimensional examples. We may look at a couple of two-dimensional examples. All right, let's go back and see how we can deal with this. Now, this is a problem. I don't know that it's identical. I think it's just similar. It says, here is an object and it has a charge and it's located right there and it's negative. Now here's another example. There's two examples right next to each other, example A and example B. Here we have a charge, same amount of charge, but oppositely charged, meaning one was positive and one's negative. So, and what's important in this example is we're looking either at part A or part B. These two charges are not affecting each other. So ignore the lower parts of this and just look here. So here's a negative charge, and what we just said was that the electric fields are going to be defined so that at any point surrounding that negative charge, there is an electric field directed towards the negative charge. And the magnitude of that, we're going to have to go in and calculate this number. Boy, we've got to go in and... Yeah, they've already done the math, so let's go ahead and see how did they get those numbers? Yeah, they've kind of given us too much information, so let's actually, I'm going to flip back and forth here. So here is the example. I'm going to start with the positive charge because that's our default, right? By convention, we start by defining everything in terms of a bunch of positive charges, and then we'll flip things around as needed. So I'm going to say here's a point charge, here is an electric field. Now if I look at different locations, the electric field is oriented differently. And so what I'm going to do is I'm going to introduce this idea of what's called a unit vector. Now you guys have been seeing unit vectors. We've been seeing these in class from time to time. In the book, they've been using unit vectors, I, J, K, to provide directional information. I was in the X direction, J was in the Y direction, and K, the K unit vector, is in the Z direction. Unit vectors, the idea of a unit vector is it has a magnitude of 1, and that means it doesn't change the amount of the vector, but it has directional information. And so what I'm going to do is introduce what's called the radial unit vector. And a radial unit vector at any location in space is the unit vector that points away from the center. So what we're going to do for these point charges is we're going to place them kind of at the center. Imagine placing them at the center of a coordinate system. And then the unit vector is just pointing away from the location of the charge. So the radial unit vector is always going to be pointing away from the charge. With that definition, I can say that the electric field vector is given by kq over r squared, and its direction is given by that unit vector. So magnitude is kq over little r squared, distance squared, times the unit vector. Now kq over r, I can plug in the value for the force constant, I can plug in the value they gave us for the charge, and then I can put the distance. Now remember, they gave all these distances in centimeters. I keep having to change them into meters, and that's fine. So I'm changing those into meters, and what I ended up with was that kq over r squared, then, notice that this is 8.99. This happens a lot. So this is 8.99. 8.9 is almost 9, right? And so what I've got is a factor of 9 here, and a factor of 3, and I got 2 factors of 3 here, canceling. And so what I'm ending up with is that 3. So a lot of times, just because 8.99 is so close to 9, you end up with something that looks like a coincidence, and it just because it happens to have that value. Anyway, the electric field we're getting is 3 times 10 to the 5th. So the 3 here is not coming just from the 3 here. It's because these other 3's were introduced. So I've got a magnitude, and then I want to get how much on the electric field. So it's 3 times 10 to the 5th. Now what's going to happen if it's a negative charge instead? What if the charge is the object is negatively charged? Well then, at point A, that's the same distance, all I have to do is take this and imagine what would happen if we flip the sign. Well, flipping the sign does not change this calculation. It just changes the direction. So once I've calculated for a positive charge what the E field looks like, or numerically what the value is for the E field, if I replace that positive charge with a negative charge, the E with the same magnitude of charge, it's going to have the same amount of an electric field. It's just going to be oppositely directed. Okay, let's see. Yeah, this example looks fine too, I think. So let's try this. What is the electric field, the E field, at a location between 2 charges? So I have object 1, now it's negatively charged, and I have object 2, and object 2 is positively charged. Now if I pick a point anywhere in space, they pick the point right there, point P, Q1 will have an influence on anything placed at P, and Q2 will also have an influence. It will exert a force on any charge placed at P. So what we can do is we can think, okay, I haven't decided yet what I'm going to place at P. Let me go ahead and just calculate the electric field so I'll know what the electric field is. So because this is negatively charged, the electric field, due to the presence of charge 1, is going to be to the left. It's going to be directed towards that negative charge. Now, let's set that aside, and now let's ask the same question about charge 2. What will its electric field look like? Now that's a positive charge, So its electric field will be directed away from that positive charge. Well, what's happening then in my vector diagram is both the electric field due to negative charge 1 and positive charge 2 are going to end up in the same direction, right? I independently looked at what's the direction of the electric field due to charge 1 and what's the direction of the electric field due to the presence of charge 2. So I determined that they're both in the same direction, and that means that what will the net E field be at that location? And it will be the combination of E1 plus E2. So again, the diagram has completely answered the question of what direction will the E field be in. What do we got left to solve for? Well, what we got left to solve for then is I got to put in the charges and the distances and find out how large that electric field is going to be. So here we go. Here's distance 1. I'm going to call that R1. Distance 2, I'm going to call that R2. It's from the center of the charge out to where, and I always call my points point A instead of point P. I think you guys are familiar with that already. So I'm going to say, okay, here's what we're asking. We're going to ask about the electric field, but then we're going to move on and ask about electric force and acceleration. So this is a really good example. So here are the charges that have been placed. And here are the distances to point A. And so the electric field, due to the presence of charge 1, is kq1 over distance squared. I got to get the right distance in there, and I got to get that converted to meters. When I carried out that calculation, I got an electric field value of 5.62 10 to the 8th newtons per coulomb. Now, what's going to happen with these electric field calculations and electric force calculations is sometimes the numbers can be really, really large. So this is an enormous number, the 10 to the 8th, and I kind of have to ask myself, why is that such a large number? And this is a large number because little k is big, numerically. That's a big number. Little k, we're already starting off with 9 times 10 to the 9, which is about 10 to the 10. Now the charge here was given in microcoulombs. That's going to scale down my numbers. But then the r's were pretty tiny. That was only 2 centimeters. So that's 0.02 meters. So it is worth kind of talking yourself through this and saying, is that a sensible result? And it looks like it is. It looks like that's a sensible number to have ended up with here. So we calculated that, 5 times 10 to the 8th newtons per coulomb. Those are the units on the electric fields. That's how much force per charge that might happen to come by. For electric field due to the presence of charge 2, now this one is farther away, but it's more charge. It's twice as much charge, but it's 4 times as far away. So that worked out to be smaller, 7 times 10 to the 7th. So what we see from the diagram is that the net electric field is going to come from taking that value for E1 and the value for E2, adding them together. So that's how much electric field I have, and its direction is going to be towards the left in my diagram. Okay? And on midterms or whatever, that's what I want to see. So just putting a plus or minus in here, it's kind of okay, but what would be better is just to be really clear about drawing a diagram and then showing, based on that diagram, which direction are we talking about. Right, pluses and minuses are going to depend on definitions of coordinate systems. Just draw the diagram and show on the diagram what direction we're talking about here. Now in part B of the problem, now this is the part that I don't think I read this earlier. That's a lot to read through. Part B says, what would happen now if we took an electron? Now the electron mass is given here. It says we're going to place the electron at point P. So I've got these 2 charges, Q1 and Q2. They're already there. They've been placed. They're just being held in place by something. So they're not going to stay there by themselves. They're going to attract. But we're going to lock these 2 charges in place, build some kind of a device, and then we're going to introduce an electron right there and let go. So if I introduce an electron to point P and let go, where is it going to get pushed or pulled? And what we've shown is that the electric fields are going to the left. Now this is an electron, and the electrons are negatively charged. So what's going to happen is the force acting on the electron can be determined by taking the charge of the electron and multiplying it by the electric field. Now I've written that in vector notation to remind myself that because this is an electric force, the force could be in the direction of the electric field or it could be opposite, depending on if Q is positive or if it's negative. If Q is a positive value, then the direction of the force will exactly match the electric field direction. But if Q is negative, the direction of the force will be exactly opposite the electric field direction. So since this is an electron, the electric field is here, the force is going to be exactly opposite. Okay, so to find out how much force, we can take the charge of the electron, multiply it by the electric field, and that's it. It's 1.01, 10 to the minus 10. The charge on the electron is pretty small. And it's going to be pointing to the right. What in the coordinate system is probably considered the positive x direction. So a force of 1.01, 10 to the minus 10 newtons, and it's going to be in the positive x direction. It's going to be oriented towards the right. So that's it. We've determined how much force is going to be acting on the electron. Anything else? I think we did everything. It's all on that diagram. Questions? Okay. Again, this is a really good example to step through. So very good example. Then the last part of this that they ask about, I put this as a separate portion. So in part C, they're asking, what will the acceleration be? If I let go of the electron's going to experience a force due to the electric field, and we've determined what that force is. Now I can divide through by the mass and determine what the acceleration is. So this still works. This is, the acceleration depends on depends on net force and mass, and we've determined the force, so now we can divide through by the electron mass. Now this is one of those crazy numbers. The acceleration of the electron is going to be 1.11 10 to the 20th meters per second squared. And your first inclination probably is, can you really get accelerations that large? And you can, for short periods of time. So it's not going to go on like this for very long, but because the electron's going to start moving really fast, and things are going to change. So let's go back to the diagram. We've really only solved for the initial acceleration. So we've really only solved for right when we first let go, that's what the acceleration would be. Because what's going to happen is, when we let go of the electron, it's going to start moving pretty quickly in this direction. It's going to feel drawn more and more towards that 50 microcoulomb. It's going to end up being farther and farther away from this. So the acceleration values will change because the distances will be different. The distances will pretty soon be significantly different, and then we have to go back and recalculate the electric field and the forces and the accelerations. So all we can really solve for here is just at a particular location, just at one location, what will the acceleration of the electron be given by? Okay. All right, so I'm going to say that was a good set of examples too. So we took a detailed look at the electric force and at the electric field, and what we've tried to do is identify simplifications. Use diagrams to simplify your life. If I can get a diagram accurately drawn with all the directions on the diagram, then I don't have to keep track of all that vector notation all the way through. And that's what this is talking about, is some suggestions. So we're going to take a look at a couple of examples of different shaped different shaped charge distributions. So now what I'm going to say here is we're not going to be doing any of these integration problems. This is actually talking about it. It's in our textbook, but this is a little bit above and beyond what we're really interested in doing. But what we want to do is just conceptually have you guys be familiar with how something like this would be carried out. But again, you can take a look through the homework, and there aren't going to be any integration problems there. If they are, take a look at them. They're going to be some of the simple examples, and on the midterms we're not going to have anything with integration. So what happens with the electric field calculations? We've outlined what the formula is for determining the electric field of a point charge. Well, what if we have an object that's shaped differently? What if instead of a point charge, I have a line of charge? I have a stick, some kind of an object, and it's uniformly charged. What we have to do in those situations is pick a point. I picked point A right here. And then what I do is I step through the sample one step at a time, and at each point I say there's a little bit of charge there. And that little bit of charge gets referred to as dq, little dq. These are the infinitesimals that you saw in your calculus 3A class. And so this is just a little bit of charge, and I can take the stick and break it into individual charges. And what we do is we take the formula for a point charge, and we say, well, a point charge formula is going to apply for just a little bit of charge, because a little bit of charge is all located at one point. And that says that at point A, I'm going to get a little bit of electric field, dE, due to the presence of a little bit of charge dq. So I took this formula, I scaled the q down so that it's dq, and that means that the electric field then is going to be dE. So that's how it's done. If we have a distribution of charges, we can always break that distribution of charge into some number of point charges, and then we can carry out integrations. So what happens here is, for the dE that we've designated, it's going to have a y and an x component. And the x component will have a cosine theta contribution, and the y component will have a sine theta. So what we've done here is show how the integrations would be set up, but we're not going to do any of them. Or what we'll do is we'll just show you what the results are for a few examples. So that's how it works. So going back to this example, let's take a look. Did I skip it? Oh, I see. So here's what the charge distribution looks like. Now, since it's all positively charged, I'm expecting the E fields will be directed away from this in all directions. So we can already qualitatively go in and kind of reason through what's going on here. Another example, just very quickly, let's imagine that we have a circular ring. So I got a circular ring, and the circular ring is surrounding the x-axis. So we're going to say that there's some kind of an axis to this circular ring of charge. And so there's a uniform amount of charge that's been placed all the way around the ring. Now in this case, there's going to be a dq, which can be a little bit of charge, at each location around the ring. And I can look away from that charge and say that the little bit of charge that they've designated as dl is going to give us a little bit of electric field directed away from its location. So again, what's going to happen on the axis is that the electric field contribution will be pointed at an angle. There will be a cosine theta component, and there will be a sine theta component. Now what we can say here is, if this ring is circular and symmetric and the charge is placed symmetrically, by the time we've integrated, by the time we've added together all of the contributions of the entire ring, all of these y components will have canceled out. All of the lateral components, all of the perpendicular components will cancel out, so we can ignore that part of the calculation. Only the cosine theta components will continue. And this is what the calculations look like. So if you're, if you enjoy setting up these integral problems and you want to look through it, that works just fine. But what we've got then is I got a little bit of Q here. Now I'm not going to use DL, I'm going to use DS. That's also a commonly used distance in calculus classes. And so I'm going to start off by saying I'm going to get a little bit of charge due to every little bit of, I'm going to get a little bit of field, electric field, due to every little bit of charge. Now in this case, at the end of the day, once I've included all the contributions, the net electric field will be directed along the x-axis. We already know that. So that problem you could see on a midterm. They could say if I have a ring of charge and I have a point P here, what direction would the net electric field be in? And then you got to use your qualitative reasoning and say, well, if this is a ring of charge and it's symmetrically placed, then right at the center, the E field would have to be 0. If I were looking at the center of the ring, because the direction of the electric fields would all cancel. But as I move away from the ring, I'm going to get these contributions along the axis pointed away from the charges, and those aren't going to cancel out. Okay, so we can already get the direction. The directional information comes from the diagram, and it's right here. So when I look for the net electric field, it's going to be along the x-axis, and it's going to come from integrating dE, but only the x component. And that's why there's a factor of cosine theta included. So the dE is going to get replaced with k dq over r squared. And then I can factor out anything that's constant. Now, the force constant is always constant, so that can come outside the integration. This is kind of a unique problem. It's not unique, but it falls into a category of where there's a lot of symmetry. And that says that the distance r between each piece of charge and where I'm calculating the electric field, that distance never changes. So little r, in this case, is actually a constant, and that can be brought outside the integration sign. And the angle theta is a constant. So everything comes out the integral sign except for the dq. And if I add all the q's together, I'll get the total q of the ring. This is on the one hand, it's kind of a trivial integration, but on the other hand, conceptually, you got to kind of stop and tell yourself why everything comes outside. In any case, what we can do then is say, well, what is the cosine of theta? And what the cosine of theta is given by is the distance x measured from the center of the ring out to point A, divided by the hypotenuse, which is r, and the hypotenuse is going, little r, is going to be x squared plus a squared, I'm using Pythagorean's theorem, x squared plus a squared square root. And so that got included too. Now, I'm not going to worry about the details of this, but this is the formula we ended up with. And if I plot that, this formula correctly tells me that if I'm at the center of the ring, all the electric fields cancel out. Notice when x is equal to 0, the electric field is 0. And then, as I move farther away, the electric field actually grows because I'm not getting complete cancellation. I'm getting a net electric field. But then what happens is eventually I'm so far away from the charge that the electric field begins to drop off again. That's all contained in the formula that we came up with. Now, one more item in there, which I don't think, what would the electric field look like once I am far, far away from this charge distribution, and it will start to look like a point charge? So I didn't do it in this example, but we would actually be able to go, well, I guess we could do that. What would happen if we got way, 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 way over here? If I get over to this point and beyond, far, far away, that distance A becomes very, very insignificant compared with x, and at some point I can begin to just ignore it as a good approximation. And what that becomes then is kq over x squared to the 3/2, that's x to the 3, but there's an x on top. Oh, that becomes kq over distance squared. So if I get far enough away from any charge distribution, it starts to look like a point charge. And that makes sense, right? The formula we have for a point charge will work for any object once I am far enough away that the extended size of that object becomes negligible. Once A is negligible compared with x, that begins to look like a point charge, and the electric field formula asymptotically approaches the formula for a point charge. Okay. Now, this is also a bit of an unusual sort of problem. What they've done is they've taken the ring that we just looked at and said, look, if the electric field points out that way and it points out that way, the ring itself is positive, what if I took a little tiny piece of something that's negatively charged? If I got a little piece of something that's negatively charged and set it just off center and let go, the forces are going to pull it to the other side. But when it gets to the other side, it's going to get directed back. So because that little piece of charge we introduced is negatively charged, what's going to happen is it's going to oscillate. It's going to get drawn towards the positive charge, but then it's going to overshoot, and then it's going to get drawn back the other way. So the question becomes, if we had, I got to check the signs on this. Okay, so they did flip the sign. Okay, I just got to make sure. We could either do this with a negative ring or a positive point charge, or very same thing would happen if we had a positive ring and a negative point charge. But let's do this. Let's go with the negative ring, positive point charge. The E fields then are directed inwards, and that says the force acting on Q is going to be minus Q times the E field. Well, that's the formula we solved in the last example, multiplied by little q. Now, for small displacements where x is really, really small compared with a, I can ignore the x squared on the bottom compared with the a. Now, I can't ignore the x on top because x on top is a multiplied factor. I can't just ignore x. I can't set x equal to 0 on top. I have to say x is small compared with something else. So in the denominator, I can ignore x squared compared with a squared. These things are added, not multiplied. And so the a squared term will dominate. I can ignore that. And it says that the force, for small values of x, this will be a very good approximation. And this takes us all the way back, if you guys remember, to chapter, what was it with oscillations? I want to say it's chapter 14, maybe. Chapter 14, yes. Where we showed that if there's a restoring force, see there's a minus sign here, with a bunch of constants times x, the stuff inside the parentheses becomes what we call a force constant. So the little k, which is actually the electric force constant, times the product of the charges divided by a to the third, that's the radius of the ring, all becomes a force constant. So k force constant is given by this expression. That gets divided through by the mass and square rooted in order to calculate a frequency of oscillation. Now, another thing that they forget to tell us in the example is that this charge isn't going to stay on the x-axis unless something forces it to do that. So we would have to have the charge inside a tube, for example, or maybe it's a bead with a little hole drilled in it on a string. Something has to prevent the charge from heading off at some angle. But as long as the charge is constrained to move along the x-axis and there's no friction and then the charge would oscillate back and forth inside that electric field of the ring. Okay. Ooh, here's an even more challenging example. Again, we're more interested in the results. I'm going to set everything up and move through it pretty quickly, so don't worry if it's making sense, great. If it's not making sense, don't worry about this example. I've tried to maybe pack in a little more than necessary, but I did want to look at this example because let's say that we have a charged disk. So this is something that you could encounter in some kind of a device. Let's say that built into some kind of a mechanical device, we have a disk that becomes charged. What will the electric field due to that disk look like? So we're going to use the same approach as before. We're going to say we're going to integrate, but this time what we're going to do is we're going to say that the circular disk can be divided up into a series of concentric rings. And so this is kind of this is stuff that you've seen maybe in calculus classes, either 3A or 3B. Each ring is going to have a charge of dq. Now, the amount on each ring relative to the total charge is going to be the area of each ring divided by the total area. And that gives us a dq expression of q, 2r dr over a squared. That is the dq that gets substituted here. Now what I can do is plot anything that's a constant. And for now, x is going to be treated as a constant. And then I'm going to carry out this integration. And again, I'm not going to look at the details. This is the formula we end up with. It says that the electric field along the axis of a circular disk is given by this expression. Notice that as x approaches 0, the electric field becomes 2kq over a squared. Now what we can also do is introduce what's called a charge per area, and the symbol for that we use is sigma. So you're going to see the sigmas getting used in this chapter. And that's the total charge divided by the total area. I can also rewrite the formula this way. So these are the two ways the formulas have been written. This is in terms of the total charge and the radius of the disk. This one has been written just in terms of the charge per area. And so that's telling me what the electric field will look like. Now keep this in mind because, well, I'm going to show you a graph of this. And so right at the surface of this disk, as I get closer and closer to this circular disk, the electric field there is given by 2, that's the force constant, times q over a squared, which is the same thing as 2 pi little k times sigma. Now that's if I'm right at the center. What happens is I move away from the disk, and the electric field drops off pretty quickly. You can see that the electric field surrounding or along the axis, the electric field, as I move away from this disk, the electric field is going to drop off. And it's going to drop off quite rapidly. If I say that A is the full radius of that disk, notice that what my plot is showing is by the time I am a distance away from it, this has already dropped down to like 30%. Right, so going back to this example, by the time I am here, so we're taking a radius of that disk, coming this far away. By the time I am here, the electric field has dropped down to 30% of what it was at the surface. So keep that in mind. We're going to see this come up again in the next chapter. But for what it's worth, that's a formula that we have developed. So this is a formula that gets thrown around a lot in the textbook, and that's saying that at the surface of a disk, there is an electric field given by 2 pi k times sigma. But to get that value, I've got to be really, really close. I've basically got to be right up against the surface of that disk in order for it to have that value, because the value actually drops off pretty quickly as I move away from the disk. Okay, so that's probably a good place to stop. We're going to come back and use this in some later examples, but I'm going to stop for the day. This is chapter 21, so there's a lot of stuff in here. We do have one more lecture that we are going to have on chapter 21.